Time dilation. So the concept of time dilation in special relativity says that time will not be measured as being the same from different reference and reference frames. So Einstein did a thought experiment. So we understand that the thought experiment is an experiment that happens inside one's mind, helps to try to figure out how to prove an hypothesis. So in this thought experiment, Einstein made us imagine a beam of light, a photon, being shown between two mirrors. Of course, it will shine forth and shine back, and it will move at the constant speed c, as stipulated by the second postulate of special relativity. C is constant, measured from any frame of reference. So if we were to quickly measure the time it takes for the light beam to go up in this distance, we may call d. We may call this separation d. We will know that speed is equal to distance over time, and therefore if we were to express the very same distance, we could express it as ct. And we did this for half the journey. We didn't do it for when the beam of light returns. Of course, that will duplicate the distance, right? And it will be ct over 2, because here you will have 2d. So for now, we're just looking at it as just one way. So in this case, distance, one-way distance will be measured by ct. Now, what Einstein said is that if we were to take this very experiment and carry it out inside a moving train, what will happen is a person inside the moving train, will confirm that the experiment works out as we see here, as we saw here first. Now, Einstein's theory of time that helps us to understand time dilation was that if you had an observer outside a train also looking at this thought experiment, for him the time will not be the same. Remember, because of the second postulate, what is constant here is c, the speed of light. But what will happen? From the perspective of the person outside a train, he will see the photon, because of the moving train, as bouncing between the mirrors in a new distance. And of course, the train itself is moving at a certain velocity, we will call v. Now, since we're talking about the photon of light, second postulate still says that the speed of this beam of light will still be c. Only thing that changes now is the distance covered. So how can we interpret this to help us understand time dilation? Well, if we were to draw the vectors, we would say vertically for the moving observer, this is how we'll see the photon moving, observer. And diagonally, this will be what the stationary observer will see of the photon. Now, of course, we also have the train moving. So according to the stationary observer, the train will move in this direction. How does this help us? Well, if we analyze the same vectors now, we analyze time using the same vectors, we could say that for the person moving in the frame of reference of the moving of the event, this is called an event. The light, the photon going up and down is called an event. So from the observation, the time taken for the event, now in this case as viewed time taken for, let's call him moving observer. So he's moving because he's in the event that is of the train that is moving. This will be the time. Now, time taken, the time taken also will be covered by this vector, time taken, but this time taken is according to stationary observer. And time taken by the train to cover the same distance, to cover distance at the velocity that is moving. Time taken by train. Why are we doing this? Of course, these lines do not represent time, but we are just saying the perspective, the frame of reference, if we're to measure time. These lines represent displacements, right? But still, for sake of understanding, we will say, so the time as seen by the observer who's in the event involved in the moving train will be called proper time, because he is inside the event. His frame of reference is moving also, just as the train. So the rest of the time will be t, normal time as seen by the observer who is outside the event. In this case, is measured from the reference frame that is outside the event reference frame. So we have only two times. So we will say the proper time is time as measured in the same reference frame as the event. The event in this case being the train moving and the photon bouncing. Now t is just the time measured by observer on frame of reference outside